some examples of like, thank you, Saram, of things to do, and then give you some room to like explore it on your own and ask me any questions. I'm definitely not like a total expert, but I've definitely done a few projects that have involved extensive simulations, from sort of stress strain and load bearing sort of questions, that actually stemmed in part from like that CAD class that we took. I built this sort of like hexapod walking robot, and I did analysis on how much load they could take before they would break or before the motors would fail. But you'll see that it's pretty easy actually to design a system that maybe will have some sort of flow around it or through it, or will be interfacing with other components like motors, or other physical objects in the world, or gravity, that you'll want to actually simulate and see how they'll behave before you actually go and maybe 3D print it or manufacture or whatever. And you can actually even assign things like, friction properties or material properties. So like if you're doing rubber on steel for whatever reason, you can sort of simulate these things together, which would be lots of fun. So we'll go ahead and get started. If someone joins us late, they can just hop on in. So by show of hands, people have used SolidWorks before? That is yes. Do people have SolidWorks available on their own machines? Great. And if you don't, you can use the link that I sent to access the Yellow Remote Desktop. But if you have SolidWorks on your own, then I'd say just open up SolidWorks, and we will get started. So I'm going to open up my own SolidWorks. So go ahead and start a new part, and we'll start from here. Let me know. Give me a thumbs up when you're here, or just give a constant thumbs up if you'd rather just watch and not like follow on your own computers. And feel free to just stop me or ask a question, because if I go too fast or too slow. All right. So first thing you need to do when you're asking any sort of simulation question is like, what is it that I want to simulate? And SolidWorks has a lot of different options for this. So if you go to SolidWorks add-ins, this tab here, if you don't see it there, it might be in File. Let's see, Insert. Where is it? Tools. I think it's in Tools. If you don't see it in like that menu, it's in here somewhere. You can even search for it. But for me, it's like this right here. And you can see it has all these add-ins in here: SolidWorks simulation, routing, motion, flow simulation. The ones that I think are the most common to use, especially for beginning out, doing some sort of like elementary, rudimentary simulations, are going to be motion, simulation, and flow simulation. CircuitWorks is for integrating things like a PCB that you've designed and seeing how maybe you want, maybe you're building an enclosure for a toy or some piece of hardware at least. And you want to analyze the heat sink, right? How much heat is being, the convection of the heat off of the part is going to melt the plastic. How is the heat going to flow out of the thing? That's a great way to use CircuitWorks, or you can use the flow simulation for that as well. PhotoView 360 is one for rendering, so maybe you want to like make something look really, really gorgeous with different scenes and textures. That's great for that. The ones we'll be covering today are going to be the motion and the flow analysis, since that's what people wanted to do, but we can also do a little bit of regular simulation if we want. At least, so this is a pretty small workshop, pretty conversational. You've been to these before. So you have experience before with SolidWorks, right, Luis? Have you done simulation stuff in SolidWorks before?
Not in SolidWorks, in other programs. So
okay, great. So hopefully this will be a little similar, and if anything, it'll be sort of a way to see how you can use some of this stuff. As we said, we're opening up a new part, and the first thing you need to do is create some parts that we're going to be working with. And the easiest example of motion to show is two things, against each other with, natural sort of forces in play, the most natural force being gravity. So let's go ahead and make make and extrude this like triangular shape like a ramp. And I'll do that just really quickly here. Front plane, we'll make a triangle, simple as we can. I'm going to go ahead and make this like 20 inches big. And then so tall. We'll play around with this angle. We'll make this like a 30-degree angle. There we go. That looks more like a ramp. Go ahead and exit that. And we'll give this a little bit of depth. So let's make this 10 inches. Let's make it like 20 inches. Cool. 20-inch ramp. Beautiful. I'm going to get rid of all these planes because I hate the planes. Awesome. Beautiful ramp. We'll save it. We'll call that, you know, basic ramp. Oops. We'll save it somewhere else. Save it in desktop, CID, SolidWorks. Basic ramp. Cool. All right, so that's one ramp done. Let's make another part real fast. New part, and we'll just make a little wheel. And then it'll literally be a circle extruded. Yeah. The point here is not like making fancy smancy stuff. It's more like to showcase the thing. We'll make this 3-inch extruded, and I realized I didn't specify the size, so let's make this. Let's make this maybe like a 5-inch circle. That seems reasonable. This is a 4-inch circle. Cool. Very basic wheel. Exit. And for the sake of delineating what's what, let's make this a different color. Let's make it like, let's see. Like a turquoise. Yeah, like an orange. That looks nice. Great. Save that. We'll call this basic wheel. Thumbs up for people. This is quick enough to follow. We're just sort of getting set up. We have another person.
I'm back.
Oh, okay. It's just Luis. He wants to get the information twice as fast. Okay. Such a stupid joke. All right. Assembly. Okay. All right. So now we're going to put the parts together. Anytime you do a motion analysis, especially with something that is involving multiple parts, it's always going to be within an assembly. You can do motion analysis and other simulation stuff in a part, but more often than not, you're seeing how two parts interact with each other. So opening up the assembly, the first one you're going to want to put in, it doesn't super matter the order, but in this case, put in the ramp first. The reason I'm putting the ramp first is because the first part you put in is going to be fixed, and you can see that with the little F in the left corner over here. If you want it to float, so right now I can't move it, right? It says it's a fixed object. And in contrast, if we insert components and then insert the basic wheel, that can move if you click and drag it. But this is not. If you ever mess that up, you can just right-click the part and click float, and that will make it movable. But in our case, we want the ramp to stay fixed because we're seeing how the wheel behaves on the ramp. So ramp, right click, fix, set, can't move it anymore. Great. So first thing we want to do is sort of set ourselves up for our neutral state, so like our null. To do that, we're going to want to like place this wheel in like at the top, for example, because we want to see how it's going to roll down. To do that, the easiest way to do that is to sort of like look directly normal to two planes. So in this case, we're looking directly at the side. So I'm going to place us up here. And then we'll look directly at this plane. So I'll go normal to this and then put it over here. So now it should be directly on top. Yeah. Yeah, it looks good to me. Does that make sense for people? Awesome. All right. And so from here, this is great. This is our basic setup, but there's no motion here yet. If you go down to the right tab, you can see that actually SolidWorks creates a motion study for you by default. And if it doesn't, all you need to do is you can go into SolidWorks add-ins and you can click SolidWorks motion and have it enabled. Mine's already enabled, but if it's like not grayed out like yours, just click it. It might take like, I don't know, 10 seconds to boot itself up. But once it does, nothing should change, but you can go over and start a motion study. And if you don't see it, you can do like right click and you create new motion study or create new design study. In this case, we want motion study. You should see a screen that looks a little bit like this. People there? Awesome. Now we can get to the fun stuff. So here we basically have sort of a timeline, because with motion, time is sort of like the x-axis that we can always sort of like go back and forth on to see how things behave over time. And the left side is where you're going to have animation, basic motion, or motion analysis. You can do almost everything we're doing with animation, but for the sake of consistency, let's go to motion analysis because that'll give you the most options in terms of analyzing how things react. You could, for example, once things are rolling, you can sort of see the stress on the ramp or the wheel at a certain point in time, and you can analyze that, and I'll sort of show you how you can, not necessarily how to do that, but sort of like what that looks like. All right, so we're at motion analysis. We're here. Nothing, all this is grayed out right here because we don't have anything set up. No, there's no forces acting on our components, and there's no relationships between them. So first thing I want to do is in this menu here are all the different things that you can add to the system or the environment. If you hover over them, you can see that this one's like a motor. This one's a spring. This is sort of like something that goes back and forth. I don't know why it's not showing up for me. If I do it by memory, though, I'm pretty sure that this one right here, this little like ball with shadow balls behind it, that's gravity. So if you click on gravity, oh, thank goodness, we're going to add this like environmental force of gravity to it. And we have to specify which direction gravity is in. Based on my design, looks like my Y axis is actually the up and down axis. So we're going to click Y. And we want this to be a negative number because the Y is pointing up. So we want gravity to go, is that correct? Gravity to go down. How do I see it?
I think it's got the little green arrow to the bottom right.
Oh, it's because I couldn't see the green arrow because your all your faces.
Oh yeah.
Perfect. So it's going up, so we actually want it to go down. Great. Gravity exists, and it's 386 inches per second squared. That's correct. If you were to change your units, you could obviously do it, 32 feet per second or whatever else we wanted. But that looks good. So now we see that the motion analysis has actually created an option for us to have a timer. And basically what you can do is anytime you change the parameters of the environment, you want to calculate what this does to the various components that you have. Things that are fixed or mated in the assembly will remain fixed and mated in the motion analysis. So if you fixed the wheel and the ramp and then you calculated the motion, nothing's going to happen because nothing's moving. If you were to mate the face of the wheel to this face and then run the motion, it'll do everything, but it'll sort of keep the mate calculations in mind. So keep that in mind if you're ever doing things with complex systems. In our case, we will hit calculate, and you should see, all right, that, and hopefully that came through in the video, but I'll show you sort of a little bit again. So this wheel right here lets you move it back and forth between the time, and then this 1x here is a playback speed. So I'm going to slow this down so you can see what just happened, and then play from beginning. It is falling, and then it just falls through the ramp. Why do you think that happened? Because SolidWorks is like, hey, we can add gravity, but I don't know, like, what is this wheel? What is this ramp? Like, they're just like figments of my imagination. So we need to make them real objects. And you can do that in two ways. You can give them, you can assign a material to them, or the preferred way, especially for the motion analysis, is to add up contact information. The way you do that is right next to the gravity, there should be one that says, now it's hovering, contact. If you click contact, it'll say, hey, let's create points of contact between two or more pieces. You can see that it has two options, solid bodies or curves. In our case, we're going to almost always want solid bodies. The two solid bodies that we want are the wheel and the ramp. You can actually see that it lets you assign different materials to these things. And what that'll do is just basically create your different coefficients of friction, both dynamic and static friction. So let's say we want the wheel to be a rubber wheel, and then the ramp is a steel ramp. And you can even see that it gives you, greasy or dry, greasy, dry, greasy, dry for different scenarios. And obviously, like, there's more than 3 material types in the world. But for approximation and the purpose of approximation, this is like a great tool, especially if you're using simulations for just like, getting a rough idea for how something will behave, or creating an animation to show off to an engineer or a client or for art or whatever that might be. So we created these 2 points of contact, we hit OK. Now we're going to recalculate from the beginning, and now we should see the wheel is rolling down the ramp. Success. Stop that, and now we can play from the beginning as much as we want. It's going kind of slow. Let me speed it up a little bit. Whee! Awesome. Any questions? Or was that successful for people? And here's where you can start to, here's where I would encourage you to sort of play around with it. So if you go back to your ramp, so let's save this assembly model, save. Come on, computer. There we go. Ramp system. I'm always worried when I do Zoom workshops with SolidWorks that it's just going to overload my computer with all the processing power. All right, so ramp assembly. So now if we go back to the ramp, and let's say we just changed the sort of angle of attack, or even had, not so what I want, had a lot more fun with it and made this into like a fun like curvy thing. We can see sort of how it'll behave. So if we go normal to it, let's turn this into like a little roller coaster. And you can pretty much bet that this is how, like, obviously they have dedicated software, but like this is how roller coaster engineers are going to like be making their coasters. It's just like figuring out what's the best way to design this thing. All right, so did that. Then I'm going to trim there, trim there, trim there, and now select exit. Cool, I have this fun roller coaster thing. Let's hope that my wheel stays all the way on the track unless I made something too steep, or the wheel needs to be a different sort of motion. Save that, go back to our assembly, ramp system. Cool. And in the same way, we want to verify that the wheel is above that. So it's above that there. We go above, it's above that there. Let's go from behind. That's perfect. Cool. So we can stick to that. We'll hit save. And it gets a little finicky with starting from the beginning. So if let's create a new motion study. And we'll make sure this is motion analysis. We'll add gravity again. It's in the Y direction, going down. Great. We're going to add points of contact. You can do this based on the other one. I'm just doing it so that we can do both. And we'll keep them both acrylic. Awesome. And that's it. So let's see what happens. Calculate motion. I'm in a workshop. I'll be for like an hour. Sorry. Great. So let's see what just happened. Restart from the beginning. Cool. It looks like it's, let me go a little faster. Rolling down the hill, and then it, fell off right at the last second. So what's nice is as you do it, you can sort of like view it from different angles and see what's happening. So there it sort of disconnected from the ramp, and then at the last, oops, fell off. And that's where you can start to sort of play around with the various things that you have there. Questions, thoughts at this point? Let's do another motion thing. Let's create a new part. We're going to create two new parts. And I'll show you another piece of the motion sort of thing that is nice and fun to use. So I'll put this over here. Let's make just like a cylinder, like a hockey puck type thing. So we'll make a circle, make it exactly 1 inch big. Cool. Exit, and this will be, let's make this, 1 inch. Oh, that's pretty thick. Let's make this like a 1/2 inch. Cool, that's fine. Awesome. So that 1/2 inch, we'll save this as the shaft. Why not? We'll make another new one. And what we're going to illustrate next is how to add motion as if you were running a motor from something. You can hopefully start to imagine that this can be very helpful if you're designing robotic systems, if you're using things. So now let's design the thing that's going to go around the shaft, so like the actual spinning, either the head of the servo or the motor or whatever. So let's do a top plane. Let's design around the shaft that we just created. So we made a 1 inch circle. Bam. Great. So we need a circle around this. It's a little bigger. Let's make this like a 2 inch circle. Great. And then let's give this so that we can see the rotation actually happening. Let's make this into like an arrow so you can sort of see what's happening. I'm going to do a quick little trick here where I'm going to go select the midpoint, go up, escape, right click that. I'm going to make it a construction geometry. You can also right click it and click for construction over here. And then I'm going to go ahead and just draw half of the arrow. So I'm going to go like up like that, maybe down, maybe back up, over, hovering up until it sort of like snaps to the center. Escape, and then I'm just going to hit mirror, select these 3 lines, and then mirror about the construction. And then you have your arrow. Then all you need to do is just trim these 2 lines, and then you have this little arrow thing. And it can be whatever thickness you want once you extrude it. So I'll actually leave it nice and thin. Is that good for people? Great. Okay. So we'll save this as arrow. Document named arrow is already open. Let's save this as arrowhead, because I've ran through this before the workshop to make sure I can do it. Cool. And as we know, we want to make now an assembly to combine these 2 things. And this time, the thing that will remain fixed is going to be the shaft part that we created. So we're going to go ahead, assembly, and insert our shaft. Boom, insert the shaft there. Great. Insert components, insert arrowhead. Great. And now we're going to do a very generic mate where we're going to mate the cylindrical surface, the round surface. Delete this surface. I guess it doesn't no matter what. And then the inside surface of the arrowhead so that it covers each other like that. Great. And then we can just make the top of the arrowhead to the top face of the plane, make that coincident. And select that. You select that. So now if we look at it from this angle, here, let's look at it from the front. The top, I mean, here we go. You can grab a part of the arrowhead and start spinning it. Buddy. There we go. You can start to spin it like that. You can sort of see that it's moving. Is that good for people? Awesome. The reason it's able to spin is because it's not fully constrained within the assembly. If I was to say, put in another block here and then say like, hey, this is parallel to this something over here, then it wouldn't be able to move. But because we have it sort of set up like this, like a super basic little spinner, it can still move around like that. Now we're going to go ahead and start our motion study. So head over to motion study 1. And here's where we're going to say, okay, motion analysis, how do we add a motor? And as you saw, you can imagine that there's a motor function right there. So first thing we'll do is we'll actually literally add a motor. And here's where it gets a little tricky, and I always get confused on. I always think I would imagine that the motor in itself is the shaft, right? And that's what's sort of going to spin the thing. Really what you want is the inside curvature of whatever's going to be spinning. That becomes the motor, right? So it's almost as if you've like created like an invisible motor, a ghost motor that's going to be spinning that curved surface. You can actually specify if you want a rotary motor or a linear motor, just like a solenoid or an actuator. So what I'm going to do is I'm going to zoom in and make sure that I select the arrowhead, but just the inside edge there. And then if you zoom out, you should be able to see a little arrow actually appear showing you which direction that motor is going in. So if you want it going that way, you can do that. If you want it going the other way, you can just click the arrow and it'll go the other way. And then of course you can select your speed. So 100 RPM, that's pretty fast. Let's make it like 50 RPM. That's still pretty fast or whatever. Click check and let's see if that works. So we'll go over here, kind of like that, and we'll hit calculate and it's starting to spin. And it's as easy as, hopefully that's really easy. Like you just be like, add a motor, start spinning. And you can imagine that as you start to add sort of more complex parts, you can literally within SolidWorks simulate, the motion of a servo motor, a robotic system that can moving its arm up and down. Sort of lots of fun. You can also simulate things like moving in sort of in real time. So let's not add gravity, but let's insert another shaft over here, and let's look directly to the top. We're gonna put this shaft like over here, and let's make sure that we're also viewing it. Yeah, we want it to be like in the same plane as the arrowhead. And let's see what happens if we add solid contact. No, not gravity. contact between the arrowhead and this new shaft. And just for the sake of why not, let's make the arrowhead steel. So this is going to get like smacked. Great. And that's all we really need. So now we just we changed our environment, so we need to recalculate, and we're going to see what happens. Ooh, buddy. What happened? He flew off into outer space. Did I add gravity by accident? Oh, it's because he is just like not there. There we go. Beautiful. Okay. Now we can see, let's go a little slower, that our handy dandy hockey puck guy is about to get smacked away by the arrowhead. Smack. And you can sort of see how things behave, and you can see that even like because it was off center, the arrowhead's starting to wobble a little bit. I know that was a little anticlimactic, but it's motion, and it's like, you know, collisions and momentum and a lot of fun stuff. Any questions here? I can stop here to let people ask. Now I know I said motion and analysis. In the analysis part, let me show you what that might mean. So let me save this and close it out so my computer doesn't freak out. All right, let's open up. This is an assembly that I created as part of the computer design class here at Yale, my senior year, way back when. It is a sort of like one-cylinder engine piston. If you just go to the model, sort of show you what this does. It's made up of several parts. So we've got the cylinder, this white block there, that actually has a hole in it that allows this piston right here to move up and down. The shaft is this section here, and then we've got two sort of like, well, that's the correct. This is sort of like the connecting rod, and this is the crankshaft, and then these are just blocks that allow everything to sort of sit in place. Without any motion analysis, I can grab just how we did the spinner and just grabbed it and spun it. We can take this shaft and sort of move it up and down and start to see how we can convert rotational motion into linear motion. It's kind of annoying that this freaks out, but you can sort of see what it's doing there. But that's kind of annoying. And if we want to sort of analyze how much torque is happening on the edge of this piston or whatever, we can do that over here. So let me just show you what the analysis looks like. Bam. Here it's spinning up and down. I'm not holding anything. And it's basically just saying, let's add a motor to the crankshaft wheel and spin it. And that in turn, because of the way it's made, it is spinning all of these other things. So show that again. Wonderful. And you can see actually that in the motion analysis, there is this like extra, like thing right here. It's like, oh, there's something else happening. What's happening there is actually that, show all plots. We created sort of like a reactionary force analysis on what? I think it was, on the hinge right here. So like on this section here. And what this is saying is, you see that it's sort of like this like repeating, oscillating thing. This is basically saying at this point in time, the force on the shaft was 0. And the reason for that is because at this point, it's right before the shaft is starting to turn all the way back up. So it's like there's no force needed to like be in its resting state. And then it quickly jumps to this peak because when it goes to here, it has to sort of pull the crankshaft up against gravity to go up to its like sort of highest position. So it goes up to the peak, and then it goes back down as it's at the peak. And then again, here it's a sort of a smaller peak because now it's working with gravity, but it still has to sort of exert force to pull it down. And you can even see like the exact numbers. So if I assign, I don't know, steel to all of these, I gave it a weight, it would sort of tell you it's exerting, this many newtons. So you can see it's exerting some, 26,000 kilonewtons, which might be too high. I don't know much about cars, but you can sort of start to analyze exactly how this thing's going to behave and where it could fail, or have some stress. You can even start to, let's see, show. I don't have it enabled right now for whatever reason, but you could also export just the motion from like the crankshaft for like this specific piece here, and then run a stress analysis to see exactly how it reacted at that moment. I forget exactly how to do that right now, but that's definitely something that you like could do. So that's sort of like a jump ahead in like where a more advanced motion analysis might look like, that you could totally do basically just building off of what we sort of did here. Pause there before we move on to flow simulation stuff, which is also different and very fun. But thoughts, questions, ideas?
I was wondering if there's a way to so in the like contact thing you could select a material, but it only had like a few options. Is there a way you can add your own material to this, or
It's
is that like a
definitely
different thing?
lacking in there. And if we let's go with my thing, Spinner. This is the one I made earlier today. Motion study. So you can actually add your own material. So if I go to like the arrowhead and then right click it, and then you go to can I not add material? If I right click it down here, yeah, it looks like within motion analysis. So like with stress and strength simulation, you can add like a very specific, you can say like 6061 aluminum T3, whatever, right? But in motion analysis, it's really lacking there. It's much more for like generalizations than specifications. I do know that SolidWorks has like an additional package that you can have like SolidWorks Pro, and then you can add any material set properties to motion analyses. But at that point, you're working with like a large scale engineering firm where like if you're doing that, like that's your job, and you're getting paid to like just do motion analysis on this sort of stuff, which is cool. But I'm not good enough to do that. Any other thoughts? All right, let's go to flow simulation next. So let's go ahead and start another new file part. So this flow simulation, that is sort of opens up a new can of worms. If you have done work or like taken fluid mechanics or fluid dynamics, you know that fluids are inherently complex systems of higher order differential equations. So whereas with the motion analysis or even the stress analysis, you basically just have a computer processing a mesh of something and running either kinematics or statics and dynamic equations on it, which aren't that hard, even though like it's a lot of computations. With the fluid mechanics solver, you have these complex bodies that need to be run through like like second order differential equations, which as we know are like not very easy to solve even with a computer. The best way to do it is by sort of like approximating and then approximating over multiple iterations and then converging on a solution by trying to optimize a specific thing. If that didn't make sense, you'll sort of see what I mean. You'll sort of see what I mean when we actually do it. But let's go ahead and get started with like, say you want to, design your own car or like a toy car. And you start off with like a very, very basic design. So I'm gonna make like a little rectangle here. Everybody can design their own car as they wish. I'm gonna make mine a little boxy rectangle, and then I'm gonna add splines. And I'm gonna say the spline is, it's gonna come out like that. It's gonna look like a, like a Ferrari type deal, and then it's gonna come, maybe loop back down and then come around and connect there. And then I'm gonna make this a little shorter because that's a really boxy car. Let's make this 1-inch toy car. let's make it a 1/2-inch toy car. That's still really boxy. Great. Oh, that's too boxy, but that's okay. I'll fix the splines. The point is not the boxiness of the car. Yeah, this kind of looks like the Elon Musk Cybertruck. That's a little better, sure. All right, we'll trim this guy, and all right, super boxy car. We'll make it give it some thickness. Cool. There is your abstract car. Kind of looks like one, I think. From here, if you haven't already, go to SOLIDWORKS add-ins, and you can, just like you enabled SOLIDWORKS Motion, and I can unenable it so that it's not eating up processing power, although that might take, okay. You can enable SOLIDWORKS Flow Simulation. Again, give it like 10, 20 seconds to boot itself up, because SOLIDWORKS gets mad if you sort of like try to speed it up. Very high maintenance. But after it starts up, it should sort of like reset the screen, and you should see a new tab up here called Flow Simulation. Click that. Now, the flow simulator is kind of picky with how you sort of.
Okay,
like,
can you repeat the last thing to enable the flow simulation?
Yeah. So if you go to, do you see this menu called SOLIDWORKS add-ins? Yep. Over here on the right, you see SOLIDWORKS Flow Simulation. Click that, and then it'll like boot itself and it's do all that stuff. If you go over to Flow Simulation, it's very picky with how it does, and luckily they give you what they call a wizard to set up the environment in sort of like an easy way. If you sort of like, I don't need the wizard, and you just click new, you're gonna have a bad time trying to find, like, make sure like, oh, I want to add this material, I want to make sure it's an adiabatic wall, I want to make sure it's X, Y, or Z. That's a lot. So we're just gonna do the wizard. Oh, please save the document. Okay, save the document. This is my Tesla Model XIV. Cool. All right, so now I've saved it. We can go to the wizard. And here's starting to ask all this fun stuff. So let's name it, Flow Simulation, Flow Sim 1. Next. The unit system is very straightforward. I'm going to use SI units. Whoops. But if you wanted to do like USA units to work with like pounds, force, feet, whatever, or whatever else, you can do that. I'm going to stick to SI. Then if you click next, this is an important screen because it's asking you what sort of flow analysis do you want to do. Do you want to do an internal flow or an external flow? Internal is it's like exactly what it means. It's flow through something, whereas external is flow around something. And generally, external flow is much easier to do because you don't have to set like boundary conditions or like where's the mass inlet, where's the mass outflow. You just have to say, this is how the flow is, and it's much easier for it to like figure out how the flow is responding around an object rather than through it. You have all these options for like, oh yeah, gravity exists and it's this component or whatever else, but we're actually not going to deal with gravity or heat radiation, any of that. We're just going to make it very simple, external flow. Next, this is where you say what flow material is being used. So in our case, we're going to put our toy car through a high-speed wind chamber. So we're going to use air, but you can see here you do have a lot of options for like ammonia, carbon dioxide, H2O. You can do Mars atmosphere, which is fun. If you were to use a liquid, you could do water, argon, acetone, different types of oils, and even non-Newtonian liquids and compressible gases and things like that. In our case, we're going to go up to air and click air, so it's highlighted in blue, and then you can click add. And you should see it appear in this sort of like project fluids thing there. Did I accidentally add water? Remove. Okay, I accidentally added water, but we want air. And then you can have the flow type be laminar and turbulent. You can also, just for the sake of like doing a basic flow simulation, we'll just leave this the same. But if you wanted to only analyze something in terms of laminar flow or how something behaves in turbulent flow, you can select one or the other. In our case, we'll say just do what you're going to do, and you can even select the humidity in the environment or things like that. It's very like robust in what you can sort of analyze with. Adiabatic wall, this just means that it's insulated. So we're not putting high heat or low heat on our car. And then you can specify the surface roughness if you know it. I don't know the surface roughness of my toy car, so we're going to leave it as 0. It's fine. And here's the last screen that we're going to want to pay attention to. So if we look at our car, if this is the front of my car, and I want the wind to blow that way, I need to reference it to the coordinate system that I have here. In this case, the positive X direction is the face, this front face of my car. So that's where I want wind to blow from. So velocity is going to be in the X direction right here. And I'm going to double click this 0 and make this maybe like 5 meters per second. So you can sort of see how wind is flowing there. If I was to do it in the Y or the Z, it would still work. It would just not be like what I wanted to do. It would just analyze flow in a different way. So velocity in the X direction, it might be different for you. So just double check like what your coordinate system is. In my case, it's the X. And now if the X was pointing the other way, I would type in -5 because otherwise the wind would be blowing from the back. Hit finish. It's going to load itself up in a couple, give it like 5 or 10 seconds. And then you should see this big box appear around your, ergonomic solid shape. So now it's opened up the sort of like project window for the flow simulation. You get flow sim 1 over here, and then down here it's got the input data, which is comprised of the computational domain. If you click it, it's this right here. The fluid subdomains, which we do not need to worry about. The boundary conditions, because again, it's an external flow, we don't need to worry about boundary conditions unless we really want to. The goals, which we will need to worry about, and then the mesh, which is not necessary, but we can mess with it. First off, is computational domain. Basically, this is just saying where is fluid flowing from, and because you need to have sort of like an upper limit on all 3 axes. In our case, we just want to sort of like make sure that we're completely covering the car. So if you wanted to and you had limited processing power, you could totally, like reduce like the heights of these guys. Come on. But it's not super necessary, especially because this is a very simple shape. It's not going to take up too much processing power. Great. If you want, you can even just right click it and hit hide. So it's out of our way. We don't want to look at it. It's kind of ugly. I'm also going to change that. So if you go to this little like red, blue, green, yellow circle with the checker mark, if you click the drop down, I'm going to click plain white because I like the way white looks on, but that's just personal preference. Great. If you go now on the input data and you hit goals, like we mentioned before, this is a system of sort of complex higher order differential equations. If you know about like the Bernoulli equations and things like that, there's all these factors that go in, such as like, pressure, temperature, velocity. If you insert a global goal, this is going to tell the computational solver for SolidWorks, hey, what are we optimizing that you're basically, essentially, what is the computer going to guess at to try and like get correct within these differential equations, and then do that over and over until it converges on a solution. In this case, you have all of these options. So you can optimize the Mach number, the density, the temperature. Since we're focusing, and this here, it's not like as important. I find it's easier to converge on things that you're already trying to analyze. In our case, all we want to look at is velocity, which is pretty simple. And you can specify, let's converge on velocity X or Y or Z. Just choose velocity and you can do average velocity. So average velocity, click, and just click that. And you can add multiple goals, but we're just gonna do 1. Now you should see GG average velocity 1. That means the global goal of average velocity has been added. And when you right click goals, you can add lots of other goals. So you can add a goal for the surface specifically or for a point on the object. I find global goals to be sort of like very generic and easy. And I'll be honest, it probably matters a lot more if you're doing like a very specific analysis to determine like what kind of goal you want to set. That's a little bit beyond the scope of this class, but for now we're just doing it so that you can run a flow analysis. The mesh is not super important. Basically, the mesh is just converting the solid object into like little triangles so that it can run simulate its like analyses on these little triangles and then converge them all together. I'm not going to touch the mesh just because it does the meshing for you. From here, we say, let's run this flow analysis. So up here in the menu, there should be an option to say run. You can also right click the flow sim 1 anywhere and hit run there as well. Here, you let it go, and then it's going to say, do you want to use, what CPU do you want to use? Because we're about to run a lot of computations at once. I'm going to use, say, leave all the options and say, use this computer, use all the cores, and hit run. Hopefully my Zoom doesn't cut out trying to do this. I shouldn't. It'll just be a little slower. As it's doing this, and the reason we chose like a very simple object is because the more complex, the more curves you have, the longer this solver is going to take. So this menu should appear now somewhere on your computer that says, all right, we're preparing for the calculation. It's kind of fun. You can sort of see the thing solving these differential equations in real time. You know, it's got 27,000 different triangles that it's running these calculations on. And it's on its 14th iteration. Now it's 16, trying to approximate like, what's the answer? Like, how is, you know, air at 5 meters per second flowing around this object? For this thing should take maybe another 30 seconds. And it should get to like 200, anywhere between 100 or 40 or 50 to like 300 iterations is fine. It'll let you know, it'll say like solver is finished once it finishes converging. I think there actually is a way to see, based on the goal that you set, how it's converging, and like it starts off like really poorly and then it slowly steeps off like that. I think it's this. Show me that. Cool. Yeah. So here it's like that's the error scale, and then as you, or not the error scale, it's like some scale, but basically it wants to converge to sort of like a straight line. And it looks like we're on iteration 70 and it's starting to converge. And we'll see that it gets a lot faster. So it's 40% done. Oh, it's going back in time now. But it should finish up. Is anyone following along and also doing it on their computer? Great, yeah. So we're all sort of waiting now, but I promise it gets faster. What are people's thoughts? There we go. Mine's looks like it's getting ready. People have specific projects in mind where you might want to use this, whether it's for like academia or for fun?
I was just wondering if you've used like, specifically with flow simulation, have you used any other solvers or like software packages? Because I know there's things like ANSYS and stuff that's like specifically purpose built for like flow simulation.
Yeah, I haven't personally. I do know that like they're dedicated for that, right? So like they solve it with great accuracy. They give you even more options than we have now. But again, that's like, I'm not going to be doing like hyper intense flow simulation stuff, so I haven't had a huge need to do that. But you definitely can. One example, here we go. Solver is finished. Great. Hopefully yours will be finishing soon. You can just exit out of that screen. Nothing should have changed. The only thing you should see once it finishes is results, and then parentheses 1.fld. Before it would have said results not loaded yet. Let's go ahead and take a look at the results. Hopefully yours will have finished soon. But if you open up this drop-down menu, you have all these fun things that have appeared. And now these are like options that you can add in. They don't exist yet, but they're basically, all the data is there. You can just say like, add this plot, and it'll add it very quickly. So let's see what we mean. If you go to flow trajectories, flow, hello. Oh, okay. If you right-click flow trajectories and hit insert, this is going to be our classic, you know, what we saw on the poster type of flow analysis. So first it's going to say, hey, what bodies do you want to see flow around? In our case, you know, maybe you're not really interested in the sides of the car. You're interested in how air is going to flow through the top, how it interacts with the front, and maybe even the bottom as well. That's your car. And obviously, if you had wheels and stuff, you could do that. But that's what we're interested in. How many individual points do you want? Let's leave it at 20. And then it's going to say, how do you want to show this data? Do you want to show it as arrows or spheres? Usually there's a lot of other options as well. And then what data do you want to show? In this case, it's going to say pressure, but actually let's see velocity, because I think velocity is more fun. We'll hit check. It's going to load for like a second or two. And then we've got our handy dandy flow simulation live there. And so let's take a look at what this is saying. Here it's saying, all right, air is coming in at red max velocity. Remember, we specified 5 meters per second was, what we were dealing with for our toy car. And as it hits the front surface, as you might expect, air stalls out and goes basically to, either very low or to zero. The top surface of the car, which is, the more aerodynamic one, is where all the speed is going into, right? So we've got high speed on the top converging down to like what looks to be like a pocket of like a really small pocket of zero air, basically zero air in the back. So what this means is if you were hitching a ride on the back of this toy truck, you'd want to sit right behind the back bumper because there's no air there. You can actually, if you right click the flow trajectories one that we just created, you can animate this and hit play. And then you can see, hopefully, I don't know how well it shows up on Zoom, but you can actually see that this is creating the animation for you, so you can see it. So this adds a little bit more information because you can see sort of how the air interacts. You can see that it sort of starts to, the air from the bottom and from the top start to converge at a certain point. And you can even see that like the air here is moving much, much slower than the air up here. It's pretty cool. If we stop that and maybe hide it, there are lots of other plots that you can start to see. So if let's do a cut plot and insert it. It's going to say, what plane do you want to do it on? And there we go. Come on, you're so close. I'm going to choose the front plane. And what is this offset? We'll leave the offset fine. Let's see. Contours, isolines. Let's see if it has contours, and we'll also do velocity. Well, check. And now we're going to see this big cut plane up here. And this basically is just another way of visualizing the data. Basically saying, high velocity around the top and bottom of the car, and with a stream of like 0 to low velocity air pocketing back here. If you animate this one, it'll sort of cut across the various shapes of the car to see how it behaves. So eventually, once it hits the end of the computational domain, it'll bounce back. This is why it's better to have a skinnier domain. But there you can see how the contours change as it moves in and out, which is interesting, right? Like you'd think that, you can see it sort of like converging and then unconverging as it goes toward the middle, which just goes to show that even if your car has like just like straight sides, when faced with head-on air, the air is still going to converge to the middle. It's pretty cool. Clearly, we can do better. We can make this more aerodynamic, but it's a good start. Another plot. Get rid of that. Let's hide this. Let's add a surface plot. This one's pretty straightforward because all you really need to do is, come on, buddy. There we go. We can add isoline or contours. I like contours better than isolines. Oh, we can add both. Great. We'll stick to velocity. Maybe we'll switch to pressure so you can see what it looks like. And let's add the surface plot on the top, the side, and the front. Actually, and also on the back. We want to do it on this side. And now it'll add those same contours, but basically directly onto the front. And here you can see, hey, no velocity change, no huge pressure changes. So here's inverted from the speed, right? So it's very low pressure up top because it has high speed versus high pressure at the very front of the car. This makes sense if you were to like stand in front of the car and like hold on to there, you would feel a lot of pressure from the wind versus in the back you would feel almost no pressure. Logical sense. Very, very fun stuff. Let's hide that. It's fun to sort of like see how different objects behave. If we were to go back to, let's make a new part just for fun. So you can sort of start to see. We're also getting close to the end here, but let's make a sketch on the top plane and let's make it a circle. Actually, rather than doing it because we're sort of running low on time, let me just pull it up. I think I already did it. Yeah, sphere. I made a fun little wooden sphere. You can add a texture to it, and say you wanted to throw this ball through the air and see how it's going to behave. Maybe you wanted to design a fun, toy that's going to be weirdly shaped, like those like fun, toys that people have. Since I already ran this, I can just hit load to load the previous results. And we can see the flow trajectory. So if we show this flow trajectory, this is the arrow behaving again surface around, like air around the ball. You can also change the arrows to spheres. And that's spheres around the thing. Similarly, we can see the cut plots here, moving around the, hello? There we go. It's going so far away. There we go. How it sort of behaves around the air. And lots of other fun stuff. Like an example of an actual like engineering scenario that we had to do. I might actually be able to open it. This is also part of the CAD class. Trace, you got robbed, man. We did so much fun stuff in that. Oh man, I hope I can Yale senior year, senior fall, 400, and it was flow simulation P set, and yeah, here it is, and it was the full assembly, I think. So we had to design a windshield for a motorcycle. That was the assignment, and the goal was, if you have your head behind this motorcycle, you got this windshield up, you don't want air to be like, like smacking you in the face when you're riding your motorcycle. This flow simulation is an old format. Oh, I hope it works. You want what we just created, like a pocket of zero velocity air right behind the windshield where you can put your head, and then the air flows elsewhere. So this is what I ended up designing. It's got like sort of like weird fun contours. Full disclosure, I did not do that well in the flow simulation aspect of the class, but I did learn. And let's see if we can load these results. Load. Oh, beautiful. I haven't interacted with these guys in like years. Flow trajectories. Let's see what it looks like. So here I created flow just around the yeah, beautiful. Around the windshield, and I added a ton of points. So here's where you can start to analyze what's going on here. So let me move this up here. Cool. So if we are driving at 150 miles an hour, which is ridiculous, you should not do that on a motorcycle, but you can start to see that, all right, air is coming in at super high velocity here. And as it hits the top of the windshield, it, most of it is, sort of deflected out on top. But a lot of the air that, doesn't make it through the bottom is going to sort of create a pocket of, here you can see 0 to 20 miles an hour velocity. So you've got this whole sort of like circular area here where one could put their head and body, 0 velocity air, whereas 150 miles an hour, you've got air coming behind you. So that was pretty fun to sort of like simulate. If you look at it from the top too, you can sort of see that it's safe there. Very fun. And so you can sort of apply this to cars. You can apply it to things moving through flow. If you are interested in checking out more flow simulation stuff, I can also see the surface plot, which is show. Bam. 0 speed there, low speed there, fun. If you're interested in learning more about specifically flow simulation, I forget how I did it, but I somehow got my hands on the like official SolidWorks like docs, which like this is what they give out to like the enterprise things. This is like a 300-page document, and it literally is like how to design flow through a ball valve, how to design heat transfer, and then getting more and more porous media, so you can design a sponge or some sort of like porous material. Hydraulic loss, that's fine. Cylinder drag coefficient, blah blah blah. Heat exchanger. Where's the fun stuff? Oh, a textile machine. Radiative heat transfer. So like lots of really fun things. Hospital room, cool. So you can do heat analysis, you can do motion analysis, electronics. You can even do how like heat is flowing out of a circuit, so that's fun. And then you can use the various parameters to like optimize your designs for whatever it is you're trying to do. So that's stop share. That's what I have to show for you guys today. Hopefully this was entertaining or enlightening as to like what sort of things you can explore and do with SolidWorks, and also just generally with sort of different simulation softwares. Now, if you use other things like Fusion 360 and Onshape, Onshape, for example, has like plugins where you can like add a plugin and then you can do like a stress analysis or a flow simulation on your thing. They're not quite as robust as SolidWorks yet because it's all sort of like cloud-based, but it's getting there. Hopefully you guys were able to follow along. That's the end of the workshop. Any questions, thoughts? Yay, thank you.
Thank you, Antonio.
Yeah, of course. Yeah, feel free to head out. You don't have to stay. But I'm here to chat more if you have any questions.